So we were just revising this, okay, locality of reference. I think we have really emphasized it. So this is your example code. Because you have a loop here, okay, there are instructions that you are likely going to repeat. So that's temporal locality, okay? Then because you read this instruction, you are likely going to read this one. So that's your special locality. Like, hence, instead of reading this instruction, you take it to the cache, you come back, you read this one. No, take the 4 next to it to make use of special locality. So what we're saying was that you could be given a program like this. Yeah. You know, you're also given we are in detail 101. So, so you could be given a code like this, and then you have, the cache, all right, of a certain structure, and then what you will calculate maybe the miss rate or hit rate. Yeah. So of course, some they make reference to main memory, some they don't, and you do calculations accordingly, but we'll see the examples. What is this one? Improving 11 cycle average memory access time means that the processor spends 10 cycles waiting for data for every 1 cycle actually using that data. What cache miss rate is needed to reduce the average memory access time to 1.5 cycles given the access times in the table below? This one, yeah. You are given other elements or other values, and you are searching for the miss rate. You're searching for the miss rate. So if the miss rate is m, the average access time is 1 plus 100 m. Setting this time to 5 and solving for m requires a cache miss rate of 0.5%. So this one there's really nothing. Okay. Yes. Because it's here. Okay, we'll open it to question. So maybe what we have been talking about really now to a large degree is what is a cache, and what principles or what environment makes using a cache, a good idea. And the main reason really is locality of reference, okay? If there was no locality of reference, meaning the instructions that we access are not predictable, like totally, okay? Then having a cache was not going to be useful, okay? Because you would build a cache, all right? Then you pull stuff from main memory, you put them in the cache, okay? Then you try to read, you try to read a word from the cache every time it's not there. Why? Because your prediction of what will be required was wrong. Please help us. Thank you. Okay. All right. So this is the next important thing, therefore, is the mapping. Okay, that is the addressing question that we spoke about. How does a memory address map to a cache address? Okay, that is very important. Of course, we made an example using the alphabet just now, but we want to look at the three strategies that are used for mapping memory blocks or words to the cache. So given a memory address, how do we know if the data item, XN is in the cache or not? Okay, how do we do that? So the mapping. If it is there, how do we find it? Okay, how do we find it? Because it's not practical to scan the entire cache looking for a word. Okay, there must be some kind of a I don't know, what is this? The data structure. A hash. Okay, a hashing mechanism. Okay, you have a key, you hash it, and then it tells you where you're actually. So there must be a memory cache address mapping scheme. Okay. An example. Yes. What is Titumela? The scheme is you look at the first letter of the surname. Okay. Yes, and that gives you the address of the cache line. Yes. The simplest way is to assign a cache location based on the address of the word in memory. Okay. Yes. Do what? Assign the cache address based on the address of the word. Based on the address of the word. So that gives you direct mapping, meaning as we saw here, as we saw in the example that we made, this example, this is direct mapping. This is direct mapping because there's only one slot. Okay, there's only one slot inside the cache where a specific word memory can be found. One. Okay. All whose surnames start with M, they will be found at the location M. Okay, that's direct mapping. Okay. Meaning the way you could do it for your main memory and then the cache. For example, when I list 0, 0, F 0, okay. Then of course, 0, 0, F 04, okay. Depending on the size of your cache now, right? Let's say a cache A which stores eight words only, okay, 8 words. So okay, 8 words. It means I need the address. How many bits? How many? If the capacity of the cache is 8, what address bits again? Yeah, log base 2 of 8 is 3. So okay, the first 3 bits, of course not the first 3, but because your memory is byte addressable, okay, but hona ha re batla bala words, okay. So how only this one, okay, how only this one, this, which is actually, this is 0, 0, 0, 0, okay, and then this one is actually 0, 1, 0, 0, okay, fine. Then sorry about that. Then let's go back to this. We're saying direct mapping. You assign the cache location address based on the address of the waiting memory. Yeah? Meaning, okay. Meaning, just like we were doing example memory interleaving yesterday. Okay? Your address, part of the bits, it was to determine the cache address. Okay? Cache address. Just like Mushala, example in area and saying a name. That's your address again, your name, okay? Then part of the letters inside the name, they identify the cache slot. So memory address, part of the bits inside the memory address, they will identify the what? The word slot inside the cache, all right? Yes. So kaha the cache keeps words and address the words, not the bytes. Thank you. And each word has how many bytes? 4. Yeah, 4 bytes. And then how many bits do you need to address the 4 bytes? How many bits? No, when I left 4 bytes, okay? When I left 4 bytes. So this is your weight, okay? This is your weight in only 1, 2, 3, 4, okay? So now, how many bits do we need to create addresses for each of these 4 bytes? No, here. Okay? How many bits? How many bits? Huh? 2, okay? We need 2. Bits, address, go meaning when I let my line here 4, okay? What I the address that you need, okay? Address the determine and minimum. That's the question. You get it? When I leave 1, 2, 3, 4, this is a word, okay? This is a word, okay? Let's come here. This is a word, okay? Then it's a byte 0, byte 1, byte 2, byte 3. Okay? Huh? What byte is 8 bits? Yes. Okay. One word is 4 bytes, which is 32 bits. So Harare memory or byte addressable. We are saying memory get this group, okay? You're gonna lay okay? Then on a row, okay? Row, then on a this, okay? So Harare or byte addressable. If each is a bit, okay? Okay, 1, 2, 3, 4, 5. Now the 80 more. 2, 4, 6. Yeah, the 8. 2, 4, 6. Yeah, the 8. Okay. Yes. If byte addressable, the smallest unit you can read from memory. Okay. But we deal in words, okay? Meaning one word, it will be 1, 2, 3, 4. The 4 lines, okay? This is like one word, okay? So byte addressable, it means each of the bytes contained in the word should have an address, meaning a sub-address. Okay? That's what I'm asking. Byte 0, byte 1, byte 2, byte 3. Okay? How many bits do you need? 2. Yes, 2. Because if this one byte 0, address atingi kabang 0 0. Enaba 0 1. Enaba 1 0. Enaba 1 1. Okay. Meaning all the words word ya editing at 00F00, okay? Ka ga yona byte starting di tlameha di go be le byte 00, byte 01, byte 10, byte 11, okay? Ha re etse tjena. This is 00F0, okay? The reason re tlotseng ya ba re tla ho 00F4, okay? Hobane ho na le dibyte mono tse kae? Tse 4, okay? Re tlola byte 4, then re qala another word, okay? Meaning ho na le di-address tse ding mono, okay? There are other addresses mo, okay? There are other addresses. It's just that those addresses, they are part of the same word, okay? When I address 0, when I address 0, F what? 1, 0, 0, F2, 0, 0, F3. And then this is a word. Okay, this is a word. And that word in a lady byte. Internally, this one, the second one, this one, okay? In a lay, canale 0, 0, F4, 0, 0, F5, 0, 0, F6, 0, 0, F7, okay? Together, this is a word. So how can I go at the word address, okay? K00 F0. Yani K00 F4, the word, okay? Yes. But the bytes, okay, F0, F1, F2, F3. Okay, exactly. So let's go back to direct mapping quickly. So, okay, I want these first two bits, then. Where are they? These bits. What are these bits? These bits. They cannot be used to map a memory word to a card slot. Why? Because the address are the bytes. Take a word, okay? Okay? Let's say cashier size what? 8. Okay? 8. Meaning 3 what? 3 bits, okay? Which means so far in fact, let's simplify it. Cache of size 4, okay? Size 4, so that what that means is that so 0, 0, 0, 0, this one. Keep byte offset, okay? Keep byte offset. Okay. Those the first 2 bits of memory address de-identifier the bytes file. Then I pedi. Okay. It's on here that we use to identify it's like the first character of your surname in the scheme say discuss. So highly 0, 0, Yahoo slot 0, highly 0, 1, Yahoo slot 1, highly 1, 0, Yahoo slot 2, highly 1, 1, Yahoo slot 3. And we have 0, 0, yeah, the same. So that's direct mapping. That's direct mapping. Meaning hang of address address again, okay? Address again. K 0, 0, FC. Kappa 1, 2, F4. Kappa 0, 1, D, E. Here's your cache, okay? Size 4. Thank you. So again, Mona ki 00, ki 01, ki 10, ki 11, okay? Mona ki di tag mona ke. Mona ki the actual word, okay? You are na 00FC. Ilo dula in which card slot? What you have to do, okay? You turn it into King C, which is what? 1,100. Exactly. Then oh, busy tena tse pedi tse. Ke byte offset tse, okay? Ha ke di tsotel. Ke sheba di feng tse. So ke 11 it means itla kae? Okay? Yeah. 4 you do the same thing, okay? 4 is going to be 0100, okay? So 01 itlam, okay? E or D, okay? Yes, which is what? 110. 110, okay? Exactly. Then key. Itla itlam. So that's direct mapping. That's just direct mapping. Direct mapping. It's like then another way is to let any memory word reside anywhere in the cache, all right? So yeah, how are these slots? You just put books on the table. It's fully associative, or you can have what is called set associative. Okay, set associative. Maybe let's summarize them quickly, and then we just look at the slides. They are quite straightforward. So this is direct mapping. Yeah, that's direct mapping. So direct mapping, each memory word maps to a unique cache slot. That's it. Meaning searching address for the design we have. You have an address, then you pull the second last 2 bits. Okay. High 11, we are slot 11, we check high the miss. Okay. Can't highly fully associative, okay? Fully associative. Actually, there's only one row. Only one row. Then in that one row, all words can fit in there. Okay, all words. Yeah. So it's one row. Maybe of address 0. Okay, address 0. Okay. Then any word can fit in that row. So what should happen? It means how only an address, you know, okay, the word you're looking for, okay? Then you compare the tag. Okay. Let's go back here so that we don't. So before we finish that, let's summarize it this way. Let's summarize it this way. When I address here, okay, this is your address. So more, this is your address. And it cover what? 32 bits, okay? Then your 2 bits, okay, byte offset. Okay? Yeah. Then depending on the size of the cache that you are looking for this case, initially 4. So then these ones will give you the cache line, basically. Okay. Your block address inside the cache. Then I just say thing. This is your tag. Okay, this is your tag. This is your tag bits. Because like Rich, you know, multiple main memory words can fit into the same slot, but if you give a words different, how do you identify them? By the tag. Yeah, by the tag. By the tag. Byte offset thing. He identified the bytes within the word. Yeah, the bytes within the like the word 00011011. You're gonna wait in on the 4 bytes. Yeah, yeah. So cover a word, then I'll get over the word, even though but inside the bytes inside the word. Okay. So that resolving from word to bytes, it's like those last two bits. Yes, that. Which one is that he's asking? No, okay. On a lay address ya memory, okay? 32 bits. Okay. Do like ha if what like a okay? If can lay, if we have something here. Let's just see if we can pull something. Yellow number of Pamoko. Did I have I not a very code here, Mr. Ramoko. Aha, fine. I want. So when I lay the instruction that I get. Each instruction it will see at what? It will see at an address. An address in like 0040000. You know, the next one is 40C04AC. Okay, it is 04AC. So main memory address it will be 32 bits. That's what we are saying. So bit itself, just as we say, libito la how, get address here how, for what is statement, okay? So part of those bits, get the address, correct? They encode addresses. So one, when I address here, the bytes within the word. The bytes within the word. Ailing anything, then the first two of the 32 bits, the first 2 bits then they refer to a 100, 101, 110, 110, okay? The is Panaga the address that the bytes within that word. Yeah, I want. Then ahead, the next ones. It's until found the address of the word in the cache. And of course, when I did talk about before, it depends on the size of your cache. If the cache in a capacity 8 words, then one of 3 bits. Okay. Yeah, for 3 bits. If it is 16 kilobytes, okay. How many bits? 16 kilo. Is it 16? Okay. Is it 16 words? Okay. Yeah. Yeah. Okay. So it means how many words are contained in 16 kilobytes? Thank you. Yes, meaning 16 kilobytes. You divide it by 4 bytes. You find the number of words. Thank you. Thank you. Then how many words do you need to address? How many bits do you need to address those words? Just to onale cache ya let's say okay? Yeah, of size 160 what? Bytes. 160 bytes. So 160 bytes means what? Okay. 360 bytes divided by 4 what? Words. Thank you. Which is how much? 40 what? 40 words. Thank you. Now you should go here. How many bits do you need for a direct mapped cache? How many bits do you need to address 40 words? Then again, log base 2, okay? Yeah, log base 2 of what? Of 40. It's all for okay. It's 6. It's 6, okay? Because at 5 you're at 32, okay? Yes, then at 6 you're at 64. So you need 6, okay? Yeah. Meaning here, monana utabale, the cache address bit will be 6. That will 6, okay? When I was talking about it's the tag. It's the unique identifier for that word. It's the tag. Who identify the word uniquely. It's like Kobata statement. Kobata is the tag, okay? So both statement, go, okay. You know, individuals whose surnames start with S can sit at slot, let's say 20, okay? So ikaba statement like aba sabelo ikaba sibeli but hona if re batla go batla, how do we know ihlile ke ena a mo re sheba ka tag, yeah, meaning go batla, okay? The tag here has go batla ke these bits, the other bits. So if the word a more, the tag next to it ke go batla, that's what we are looking for. That's the person we are looking for. All right, you pare okay, let's look at them. Let's look at them. Okay, so there are key parameters that define a cache. Okay, I think already there's a hint to them. So one but let's start with one, okay? A block, okay? Like a block, okay? A block, okay, a group of words, okay? That you pull from main memory into the cache. Fine. So direct mapped cache per line of the cache, okay? Ibuluka only one word, okay? One word, meaning all the blocks are spread across the cache lines. But other structures or other schemes, multiple blocks, you can do in one line, okay? So you have a block, okay, combined together do for a cache line, like this is a line containing n blocks, okay? And then the number of lines of the cache will give you the number of sets for that cache, right? The number of so of course this is what we just did now. Okay, this is what we just did. So these bits would decide to uniquely identify the words and the blocks. The rest is the tag. Valid bit later. Okay. This formula it captures the capacity of your cache. Okay. It captures the capacity of your cache in terms of bytes. Okay. So C is capacity, and the capacity is what? The number of sets, which is the rows, again, multiplied by the number of blocks in each row, again, multiplied by the size of one block. Okay, we talk about the total bytes. Okay, we see it again. Yeah, C is equal to S. S is the number of sets, and the sets are the lines. Okay, and then N key the number of what? Blocks per line. Okay, then B key the size of the block. Okay, so for a direct mapped cache, okay, the number of blocks in one set is one. Agena batwanga tabadulang location at the same time. That's what we said, okay? For a fully associative, okay? Sorry, guys. Let me just. This guy. Five. Four. Okay. Maybe have it's a modifier just quickly. Okay. Can I direct cache again? Yes. Yeah. So can I direct, okay? Can I fully associate, okay? Then can I set a source, okay? Set a source. It's it. Direct. This is how it looks, okay? Each and every, okay? So what I will say, and Mona. Yes. Yes. 16 kilobytes, yeah. It's not 16,000 bytes. Oh, yes. So they can divide 65.4 thousand bytes per word. You divide it by 4 bytes because I just, okay. If it's, it has 16 kilobytes capacity of cache again. But also on it tell the words take. So you divide it by 4 bytes. Yeah. What you get is the number of words, okay? Then those number of words, therefore, how many bits do you need to address them? Log base 2 of that number of words. Yeah. So direct mona na mori in highlight mono, okay? Who did you what? Who did you one word? Okay, one word, you know, meaning the number of blocks, okay? The number of blocks, they are spread across all the sets. The total number of blocks per line, okay? Exactly. But directly each, okay, sorry, then I lay the sets here, okay? The number of sets, number of blocks, the total number of blocks, okay? So S is equal to B. S is equal to B. Okay? B gives you the block size of the cache, okay? Yeah. Says the number of cache lines, okay? But because directly per set, it means all the blocks are sitting on each set, so they're equal. Fully associative. Onale, the number of blocks per line. The total number of blocks in the cache. Okay? And H2, we sit on that set, meaning in only one set, okay? One set, give fully associative. So the number of blocks per line the total number of blocks, and S is equal to what? To 1. There's only one set. Okay. Set associative e kopanya di le pedi here. Okay. O so ra no, okay. E ke dumelle 2%. Okay, so get two-way there, that okay. Two-way associative or 3% or 4. Okay. So set associative e ka ba tjena. Ka fumana hore e tla ba tjena he. Ebe ho tjena. This is your tag. Then yes, ngwaneso. A block is made of words. Polaritze. How bala from the cash? Spoon, which is a word, okay? How bala from measurement, which is a word, which is a block. How bala from the hard disk, which is a page. Which one? Which one? Which one? To be super guy, okay. One more. No, it depends on 00FC. Key memory address. It attached 2 bits. Because this is 4444 again. But I calculate, okay, that address only tag. Only BDD identifying the cache the word address in the cache. You don't know the bits the byte address in the word. Yeah. So then I get byte. Cache slot, yes, for the words. So how do you address not the addresses. Whatever that we read from these addresses together, keep block. That's why in the Gita, I want to share more. ORIS2 1, 2, 3, 4. These are instructions, okay? How do you get 4? The instructions, that's a block. But each of these instructions in a lay address 13. Yes. So a block will be a group of words, and a word could be an instruction word or a data word. Okay. Yeah. Can I read this one? Okay. Yes. So set associative key hybrid directly fully associative. Okay. So it's Monan in one line. How is the a two-way. Okay, two-way. So the number n will be what? N. And then I get the number of blocks per line. Okay. Yes. It will 2. Okay. The number of words per line. Okay. Yes. Number of words per line. Get 2. Meaning monana also tete is a legend, okay? It's a legend, okay? And here slot is a Sitawina le tag this word, okay? You know, the bits starting for the offset, and the same thing the other one, okay? The same thing for that. Set associative basically mingling directly fully associative. Also depend on multiple words. Cover 3, cover 4, cover, okay? To sit on one line. Yeah. sit on one line. So this picture just summarizes everything, okay? Yeah. Number of blocks per set, number of sets. Yeah. Direct maps, okay. There you go. N is 1, so S is equal to B. Set associative, N is greater than 1. So the number of sets kaofela. Or if manager will divide all the blocks in the cache by the number of blocks per line, and then you find the number of sets. Fully associative, N is equal to B. S is equal to what? One set. Yes. Yeah. No need to yes. Okay. Okay. S. The total number of sets, the lines. A set is a set of blocks. Okay, it's a set of blocks. Yeah, a block. It's a block of words. Block of words. Yes, a block of words. So, example, we could say to direct. You could just oh, Hannah, like all that corporation. All that corp. But I read good reading, eh? You see this example, if Peter was with this, Peter was with it. Give me, this is your main number room, okay? In this other thing, this is a byte offset, okay? But cashier set direct mapping of size 8, okay? Then this additional 3 bits, you find a set ID, okay? Yeah. So then only 00, you have set 0. 001, set 1. 0, okay? And although the addresses are changing, but this cyclic, they are cyclic. Okay? They are cyclic. Yes. Daddy? Byte offset. Byte offset is are you also a word? It's one way. Okay? Yes. What are you trying to do? Example improper. Only way to say by the bytes. Okay. Let's say only a string or a string is okay. And each of the characters is a byte. Okay. Exactly. Let's say that string fits in one word. Okay, so you read the word from Kobata can fit in, no, can't. 2 words, fine, 2 words. You read 2 words, but Ubata auto capitalize Kobata, right? Right? Meaning we have access now to byte, KH, okay? Byte, okay? The processor will use the byte offsets to pick bytes within the word, okay? K if it would be the first is 0, because it's byte 0. H is 0, 1. It's to address the bytes within the word. Example, guys, kopale le skela mphoqa he. Di entse di na le dikarabo. Tla bona ntse di pheta fela. Bona ke eo. Byte offset, the set, the tag. Chevala jwang, okay, direct. Okay. No. Assignment really. Hey. Oh, I don't know. Yeah. Which of you very That example MIPS. What about it? Yes, that's what I wanted to make into the assignment, but they're classing now and you want like re together, okay, and then even in listen because like you want to for example that's like so really batswadi ba lisa dibakeng ka festing. All right, but are you saying okay? I because we can't meet Usan. I mean, Usan that's Friday. Eh? Yeah, it's Friday. Who are high? Yeah. But basically, assignment okay. Like, yeah, just 2 minutes. Assignment. Ne ke batla re tlo e discuss. Le tjho hore na se ya khona.